Hello everyone. Uh, in this video, we will be seeing regarding how TurboQuant on Qdrant Edge. Okay, like same recall, but the main part is 8x less disk is used. Okay, so this would be an honest benchmark, and in this video we will be seeing how Qdrant is using TurboQuant on Qdrant Edge. Okay, so basically, Qdrant shipped a new quantization method called TurboQuant, claiming the same recall as scalar quantization at half the storage. That's their server. Nobody run it on Qdrant Edge, the embedded on-device version, and shown real numbers. So that's this video, and I am going to warn you now. About 6 minutes in, I found something that means the videos own title needs an art risk. Let's get there properly. Okay, so now let's go through once the Qdrant website where I will be showing you regarding this. Okay, so here we can see and next we will be moving towards the Edge website where all the things are there. So basically, Qdrant is a vector database, stores embeddings, finds the nearest ones, usually as a server. Qdrant Edge is embedded like SQL Lite but for vector search. Runs inside your app process, no network hop, no background service, just a self-contained shard folder on disk. Okay, so let me show you one image regarding that. You will be understanding very well. Okay, so here we can see that how once the side is for Qdrant which is using with server, and one the side is for Qdrant Edge. Here we can see that how our device which we are using is connected with the server, and how it takes the time to scrape the data and come towards the device. Okay, and when it talks about Qdrant Edge, all the things are in your device and also running totally offline without any network. Okay, so here we can see that everything is happening in our device itself. And one thing to tell is that yeah, so that last part matters more than it sounds, because it's just a folder. We can crack it open and look. No black box. We will actually do that twice in this video. Okay, so moving forward, I will show you regarding a Qdrant page, regarding Qdrant Edge, where more things are there. Okay, so here you can see that on Qdrant's documentation part, here the TurboQuant quantization is there, in which you can see that yeah, how quantization shrink vectors instead of 32-bit. Okay, float per number, you compress it. TurboQuant is Google research method added in Qdrant 1.18 version. Okay, so rotate the vector randomly so its values spread out evenly. Then quantize each coordinate against one universal lookup table. No training, no calibration. Works the same on any embedding model. And here you can see that yeah, TurboQuant is a quantization method developed by Google. It operates by applying a fast random rotation to vectors before compression. Okay, so here we can see that the encoding bits are bits 4, bits 2, bits 105 and bits 1, and the depth and the compression is 8x, 16x, 24x and 32x. Okay, so yeah, and now I will be showing you one image regarding this only. One second. Yeah, so here you can see that step one we are choosing the original vector. Okay, where all the vectors are there. Second step would be the random rotation, and third step quantize the code book. Okay, so how it is like 4-bit depth ship, 4-bit, 2-bit, 1.5-bit and 1-bit per dimension. Quadrant's own server benchmarks look great. Nobody's tested this on Edge. That gap is what this video fills. Now let's start with the implementation part. First, I had created the environment, so just activate it, like dot env slash scripts slash activate. Okay, so yeah, once the this is activated, so like now let's first install the requirements. So basically uv pip install -r requirements.txt. Okay, and yeah, once the requirements are installed, and I will show you like what are the requirements here. So basically Qdrant Edge, NumPy, matplotlib, and sentence transformers. Okay, so yeah, I will be showing you regarding that all the packages are installed here. And after that, like let's just check first regarding python env underscore check dot py. Okay, so here we can see that the Qdrant version is 0.8.0, and the TurboQuant bit size values are bits 1, bits 1.5, bits 2, and bits 4. So distance values will be cosine, dot, Euclid, and Manhattan. And the same things which are here also, the distance metric support. Okay, see, cosine, dot, Euclidean, and Manhattan. Okay, so all the distance metrics are also on the documentation page. And yeah, once this is done, so yeah, now we will see regarding like before any benchmark, the arithmetic x times smaller should be provable on a napkin before it's provable in a chart. Okay, so yeah, I will run a command regarding the math part. So basically python, it's the file main.py and double hyphen, that is math hyphen only. Okay, so by running this, what here will be shown, okay, is we can see that the normal compression math for dimensions are 384. So basically number of bytes per vector, and how much times smaller it should be with float 32. Okay, so bits 4 is like 192.0 bytes per vector, it is 8x smaller, and then goes to down till bits 1, that is 48.0 bytes per vector, and that is 32x smaller than float 32. Okay, and yeah, so here is that. And once it's there, so basically a 384 dimension embedding costs 1536 bytes at full precision, drop to 4 bit and it's 192 bytes, the honest 8x. Notice there are two different 4 bit rows here, bits 4 and turbo for data type. Same math, same 8x. They are not the same thing on disk. That's the whole next section. Okay, so yeah, here we'll be running once again the envcheck.py, where Edge is a beta API. This confirms the classes my code depends on actually exist in whatever version is installed. Okay, yeah, and yeah, so I will be seeing you one thing regarding config file, and that would be cat config.py. So what output here, okay, one second, yeah, so what output here shows is 20,000 vectors, dimension 384, sweep should be float 32 baseline, so 4 TurboQuant bit depths and one more entry TurboQuant data type, which is going to matter a lot in about 90 seconds. Okay, so yeah, as shown in here, here's what I found while building this. There are two completely separate ways to shrink vectors. Okay, shrink vectors in a Qdrant Edge, and they solve different problems. Let's build one shard each way and just look inside them. Okay, so yeah, we will be now shifting towards building the shard, and the command for that is python, the file in which it is main.py, and same thing as we did with math, that is build and only. I think now this should work, as we had loaded the data set for that. And here we can see that building edge charts for quantization settings. And here it is running on as like the part which is going on here is 193.52 MB or 197.42 MB. And yeah, so here we can see that all the things are running properly, and we had created the shard for that, and each and every has the all 20,000 vectors which are totally, and the size for the disk here should be like variable, and like 193 or 197 or 195 or 194. Okay, so that's how it is running. And one second. And for this we can see that yeah, 6 shards, float 32 baseline, 4 turbo quant bit depths, and turbo 4 as the storage data type instead of a quantization config. Watch the disk numbers as they print. The 4 turbo quant configs barely move, and turbo 4 is visible smaller. Let's find out why. So the next I will show this. Okay. When starting with the vector storage dense, here the code will be like the get children path, and then where it is stored and what object we have to find. Okay, so once we will be running this, and here we can get that where it is stored in the directory and at what time, and the vector storage dense. Okay, so here it how it is working. And yeah, so after that, when shifting towards this, like the cat ground truth dot py. Okay, so once I will be running this, here I can see that yeah, the top k neighbors computed in NumPy and from future. Okay, so here it is stated that this is the ground truth. Every quantized configs recall gets measured against. Okay, so a bug in the edge float 32 baseline can't silently inflate every method's recall number. Okay, and when I will be running the main thing. Okay, yeah, so the main.py. So yeah, here also the edge shards for each quantization settings will be running. And once it runs, we will be getting the output as one second. Yeah, so yeah, as it runs, here we can see that the disk size would be this, and all the recall settings are here, like the benchmark recall plus latency per shard. Okay, and as the report generates here, we can see that all the images and the CSV are created. And once we go towards the image part, and one final image will be there. And here we can see that one more thing, before we run the real benchmark, these files are memory mapped and pre-allocated, reserved on disk without real zeros written for the unused part. So yeah, and this as we run the main.py, we got the images, and starting with the disk size bar. Okay, so here the comparison between the models, like float 32 data types, TurboQuant 4-bit, TurboQuant 2-bit, TurboQuant 1.5-bit, TurboQuant 1-bit, and Turbo 4 data type. So basically all the data types and their comparison, like the disk footprint by quantization settings to on disk size. Okay, so 6 bars now, not 5. The 4 TurboQuant configs should cluster near the float 32 baseline. That's the 2 copy problem we just proved with. Find turbo 4 should be the 1 bar that actually meaningful smaller. If your chart doesn't show that split, something's off. Go back and check quant configs.py. Okay, and then comes the second image, and that is recall and disk comparison. Okay, so recall versus on disk size, Qdrant Edge plus TurboQuant, where all the points are plotted, and here you can see that this chart now tells two stories at once. TurboQuant configs trading, latency for recall at nearly constant disk size, and Turbo 4 sitting at genuinely lower disk with whatever recall it gets on its own. No rescue pass available, and state plainly where turbo 4 landed relative to bits 4 on both axes. Okay, and then comes the third image, which we had generated all the three with the help of matplotlib, and here we can see that latency versus recall. Okay, and here we can see that all the data types are plotted, and whether turbo 4's latency looks like the no rescore configs, since it also has nothing to rescore. So every numbers in this CSV, like the final CSV is there, and in this every numbers rerun it yourself and check my work. That find command from 10 minutes ago works on your own results too. Okay, so yeah, that's it. And three honest caveats: one, quantization config and data type equals. Turbo 4 solve different problems. Don't reach for one expecting to others benefits. Two, at small scale, fixed overhead swamps everything. These numbers need real scale to mean anything, which is why this ran. At 20,000 vectors, not 200. 3 quadrant edge py is beta. Run envcheck.py before you trust any of this on a different. Okay. So here's the full codes. I will be sharing all the full code in the description, and so also go through once the documentation part of the quadrant 2, where you will be seeing all the things regarding here you can see that, yeah, turbo quantization, the encoding options and all the bits are there, and the compression ratio. Okay, that 8x, 16x, 32x, 24x, and all of that. Okay, so that's it, and that's the whole TurboQuant quantization we are looking for in this video. Okay, so thank you for watching, and do share, comment, like and subscribe if you get to know anything new or anything uh, better in this video. Okay, so yeah, thank you.